see iron is oriented in such a way, the tensile stress is applied along 0, 1, 0 direction. That means along y direction. Right? And this is the plane that we are talking about. This is the direction in which we are applying the load. And this is a normal to the, this is guy is normal to the plane. And what we are asked to do is compute the resolved shear stress along 110 plane. That is this along that plane in the direction and in what I think 1 minute. Yeah. And in that direction, in 1 bar 1 1 direction, that is along this diagonal direction. Sorry, in this body diagonal direction, 1 bar 1 1 direction. So we have looked at the phi is the angle between the applied loading tensile axis and the normal to the plane. Because it's a cubic crystal, the indices of the plane themselves will become the indices of the normal to the plane. And lambda is the angle between the loading axis and the slip direction. This is the slip normal to the slip plane, and this is the slip direction. So we have calculated those angles and cos 45 and cos 54.7, and then we calculated the resolved shear stress to be 21.3 MPa. All right. So you're able to see my pointer, right?
Yes, sir.
Yes, sir.
Yeah. So if you are applying 52 MPa in that direction, the resolved shear stress is 21.3 MPa. So it is given that the critical resolved shear stress, that means the shear stress at which the yielding occurs, is 30 MPa. Because this guy is less than the critical resolved shear stress, if you apply 52 MPa, the yielding will not happen. All the deformation will be purely elastic. Now the question is, what should be the value of sigma such that there is yielding onset of it, the yielding initiates. That means you need to calculate sigma for which resolved shear stress will be 30. And that is what we have done. So sigma y, that will be the yield strength. 30 is the critical resolved shear stress will be that. So that means by applying this, you will have this resolved shear stress. That means if you apply 73.4 MPa, you will be able to initiate yielding. Is that clear? Is there any question here?
Yes, sir.
If the applied stress is more than 73.4, what will happen, sir?
Normally what happens is you will not, so if you look at the previous stage. It is good a shear strain control experiment. Okay?
Okay.
Yeah. So now, if you talk about, so far we have talked about edge dislocations, and if you have a screw dislocation, we said that because the slit moves that way, that means the displacement along the slit, there is a displacement is only along the slit, that means only in Z direction. For a screw dislocation, Ux and Uy become 0. And you will only have shear strains. The normal strains become 0. There won't be any normal strains. You will only have shear strains when a you have a pure shear dislocation because the displacement field is such. And from there, you can calculate the shear stress field around the dislocation. Whereas in the case of normal dislocation, you have, edge dislocation, you will have both normal as well as shear stress components. Okay, that is something that we have discussed in the last class. So when you have edge dislocation, the stresses, normal stress, shear stress will always be present. So we have talked about the plastic deformation through something called slip. Slip is nothing but dislocation motion, isn't it? That's what we have discussed in the previous class, and also so far whatever we have looked at, this is all about dislocation motion. But in metals, particularly crystalline materials, you can also have plastic deformation happening through another very restrictive mechanism called twinning. It is a mechanism through which you can also have plastic deformation, which is very different from dislocation motion. And this is one of the most important mechanisms after slip. So what happens here is that you will have the atoms moving in a concerted manner, but resulting in a permanent deformation. But the atom displacements occur in such a way that there is a mirror image. So what do we mean by that? So for example, let us say this is your crystal, and if you are applying a shear stress, and let us say this is your twin plane, like we have a slip plane, you can have a twin plane. And if you carefully observe this atom, if I am doing shearing, this atom will move relative to this plane in such a way that after the deformation, this atom will become mirror image of that atom. You can see here, this atom has moved effectively here. So about the twin plane, you will have a mirror image of this fellow on that side. This fellow's mirror image is here, this fellow's mirror image is here, and so on. So you can actually have a shear force that can produce atom displacement such that on one side of a plane, that is what we call twin boundary or twin plane, atoms are located in mirror image positions of atoms on the other side. Right? So you can see that in here, the open circle atoms in the described by open circles, they have not moved, but the dashed lines or solid circles, they have actually moved from that position to this position, so as to have a specific arrangement of atoms wherein about that plane, these atoms will have mirror images. This is a very restricted motion, and it is not observed as predominantly as your slip or the dislocation motion. But this is also one of the mechanisms in which your plastic deformation takes place. So generally, because it's very restrictive, the stress required to form a twin is usually greater, but it is less sensitive to temperature. Whereas we have in the dislocation, the slip, if you increase the temperature, it is much easier to cause slip. Whereas deformation twinning happens in SCB metals at very high strains and low temperatures. FCC metals, primarily face-centered cubic metals like aluminum, copper, gold, and silver, these kind of metals deform primarily by slip, but they can also deform by twinning at very high strain rates and at very low temperatures. If you have temperatures are very low, that means you don't have enough opportunity for the dislocations to move easily. And if the strain rates are so high, that means you don't have enough times for the dislocation motion. In those scenarios, you can have plastic deformation taking place through twinning. Okay. So this is how you will see a twin microstructure of a twinned tungsten, which is represented by these serrations. So just for this class, you just know that slip is not the only mechanism. That means dislocation motion is not the only mechanism by which plastic deformation takes place. you can also have another mechanism called twinning, which is also contributing to plastic deformation in metals. Okay. So if you look at slip, the surface features will look something like this, whereas for twinning, you will have twin planes about which you can see a slip, the plastic deformation taking place. So for slip, what happens is the crystallographic orientation above and below the slip plane is same. Before and after the deformation, the crystallographic orientation will not change below and above the slip plane. Whereas in twins, the crystallographic orientation will change above the twin plane and below the twin. And as you know, in slip, usually slip happens in integer multiples of intraatomic spacing. So Burgers vector will be either one atom intraatomic spacing or two intraatomic spacing. That means it happens in integer multiples. Whereas twin can happen in less than an intraatomic spacing, because as we have seen, twin requires. So here it has not moved even one intraatomic spacing. It has moved more or less half the intraatomic spacing. So in twinning, the deformation, the twin displacement is less than an intraatomic spacing usually, whereas slip occurs in the distinct atomic spacing in multiples. So that means integer multiples of various atomic spacings. Okay. All right. So far what we have learned? We have learned that in metals, you have some crystal structure, and that crystal structure is never perfect. You will have different kinds of defects. One of there are two kinds of defects that we have looked at so far. One is a point defect, and the second kind of defect is what we call line defect or dislocation. And these line defects are most prominent because they explain one of the popular deformation mechanisms called slip, or popular plastic deformation mechanism called slip, which is basically the dislocation motion through the crystal. All right. And we have also learned that, okay, it is not that only slip, it is not that the slip is not the only mechanism that causes plastic deformation, but there is also another mechanism called twinning, which may also cause plastic deformation. However, twinning is a rare phenomena because only under twinning takes place. Otherwise, slip is more prominent phenomena in ductile materials. Okay. All right. So in the previous class, we have discussed about this fellow. You have a single crystal material. In the stage 1, typically what happens is you have several slip systems in a single crystal material. And when you are loading the system like that, up to here it is purely elastic deformation. By the moment the shear stress reaches critical resolve shear stress, one of the favorable slip systems, because each slip system is oriented at a different angle depending upon in which angle you are applying the load. Is that clear?
Yes, sir.
Yes, sir.
So you have several slip systems and one of them may get activated. All right. Once one of them is activated, then it is you have reached the barrier, and then you will see that at a very small increase in stress, there is a large strain. That means this is what we call easy glide phenomena. And after that, what happens is other slip systems get activated, because when the slip is taking place, the orientation of the crystals is changing, and as a result, the new slip systems become active, and hence the dislocations start moving in other slip systems or within the same slip system. When there are so many dislocations that are moving, it is possible that these dislocations are hitting each other. And then these dislocations interact with each other. There are two mechanisms that the dislocations can interact with. That is, one, if the dislocations of opposite sign come together, then they attract each other and then they annihilate. That means there is no dislocation motion. It becomes a perfect crystal. That means you have reduced the dislocation motion. That means you have reduced plaster deformation. Now, the second one is if the dislocations of opposite sign are coming together, then they repel each other. As a result, you will have a resistance to dislocation motion because your external applied load is such that two opposite sign dislocations are supposed to move towards each other. But because of the local stress field around those dislocations will not let them move close to each other. And that means you have internal resistance to dislocation motion, and that is what we represent by stage 2, what called strain hardening or work hardening. This is primarily in a single crystal. It is happening because of the interaction between the dislocations, dislocation interactions. And sometimes if two dislocations, we have discussed when will two dislocation combine, right? The two dislocations combine when the combined energy is less than the energies of individual dislocations. I think that is something that we have discussed in the last class, where if the first dislocation's energy is first dislocation is represented by Burgers vector B1, second dislocation is represented by Burgers vector B2, the energy of a dislocation is given by 1/2 GB square. G is a material property, that constant, so U is proportional to B square. Meaning, if you have one dislocation whose Burgers vector is B1, the energy of that dislocation is B1 square, and the second dislocation is B2 square. So the sum total of these two energies is B1 square plus B2 square. Now the question is, when do these dislocations, whose vectors are represented by B1 and B2, combine and form a new Burgers vector B1 plus B2? This is a new Burgers vector. That means they combine to form a new dislocation. When do they combine? They combine only when B1 plus B2 whole square is less than or equal to B1 square plus B2 square. Only under that condition they combine, otherwise they do not combine. If you have two dislocations approaching each other in such a way that if they combine, if their energy is going to be greater than the individual energies, then they will never combine. That means the dislocations are not going to form a new dislocation. That means they are not, the situation is not favorable for them to combine, and hence they get locked. And such a lock is called Lohmer lock, and then that blocks further slip. So these are the different mechanisms through which the strain hardening or work hardening takes place in a material, in a single crystal material. Okay. However, now let us imagine a scenario. You don't have a single crystal material. Now let us say you have a polycrystalline material. If you have a polycrystalline material, then what happens? You have a grain 1 and grain 2. Grain 1 will have one orientation, crystalline orientation. Grain 2 will have another crystalline orientation. Grain 3 will have another crystalline orientation. So each grain is a single crystal. But typically when we look at polycrystalline material, you will have several of such grains. Each grain is oriented in its own way, that very random fashion. Correct? So now we will discuss about what happens when you have such grain boundaries. Right? So here we are going to talk about strengthening mechanisms in a polycrystalline material. We have discussed about one strengthening mechanism in a single crystal material when the dislocations interact with each other. That is when the materials gain their strength. They become more and more stronger. Now, when you have a grain boundary in a material, what happens is at the grain boundary, the crystal orientation and the slip plane in that grain is that. So there is an incompatibility at the point where they are meeting, these two grains are meeting. And hence, the dislocation which was otherwise moving happily and nicely in this grain will see a barrier here when it hits a grain boundary. And then it becomes difficult for this dislocation to break open the grain boundary and move into the next one. For it to do that, you need to apply extremely high energy so that the dislocation can either break open the grain boundary, or you could create a very high stress field around the grain boundary such that you activate a dislocation in the neighboring grain and continue the plastic deformation. Okay. So here you have two grains which have different orientation. A dislocation passing into grain B will have to change its orientation. And in order to change its orientation, you need to put more and more energy. So what is the moral of the story? The moral of the story is when a dislocation encounters a grain boundary, the dislocation motion gets stopped temporarily. What is the meaning of dislocation motion getting restricted? That means you need to apply more effort. You need to put in more effort in order to continue plastic deformation, which means you need to apply higher stress in order for you to continue the continue the plastic deformation. And that is what we mean by strengthening mechanism. That means the material which could yield at a lower stress up to here now requires a higher stress in order to continue the plastic deformation. And that is what we call a strengthening phenomena. That means the material behaves as if it is stronger than what it was. Is that concept clear to all of you?
Yes, sir.
Yes, sir.
Yeah. Okay. So now you have this grain boundary is another kind of defect in a material. Right? A line dislocation is a one-dimensional defect, whereas grain boundary is a two-dimensional defect because it's an area, right? As a surface. So this is a two-dimensional defect, and a one-dimensional defect like dislocation interacts with a two-dimensional defect like grain boundary. Then you have the dislocations gets piled up, so near the grain boundary, and that introduces some strengthening into the material. Okay. Now, depending upon the difference in orientation of adjacent grain boundaries, you will have more resistance or less resistance. If you have a high angle grain boundary, then it will be difficult for the dislocations to pass through the grain boundary. If you have a low angle grain boundary, then it will become much easier for the dislocation to traverse to the grain boundary. That means you don't need to put in much effort. So depending upon the kind of grain boundaries, you will have your strengthening taking place. Now, so what we said was, if you have a dislocation and if it is moving in a polycrystalline material, if it hits a grain boundary, then what happens? The material strength increases. Is that concept digestible to all of you? Is there any question there?
It's clear, sir.
Yeah. Now, okay. If that is the case, if I have to increase the strength of a material, what can I do? I just need to ensure that there are more and more grain boundaries so that every time the dislocation tries to move, it hits a boundary, and hence it will have resistance to dislocation motion. That means it will not be easy to plastically deform that material. Agreed? So, if you have more grains, meaning if you have the total material is constant, but if you have to have more grains, that means the grain size is smaller. So a fine grained material, that means where the grain size is smaller, is harder and stronger compared to coarse grained counterpart, because in a fine grained material, the total grain boundary area for the same volume for a fine grained material is going to be much larger because there are more grains. And since the grain boundary area is increasing, and hence the material is considered to be, material behaves as if it is harder than a coarse grained counterpart, right? So this is a very interesting observation that people have looked at, and then used this concept for nano engineering. Meaning, what people have done is, okay, now I learned that if I reduce the grain size, I can increase the strength of the material, right? So if I have an extremely ductile material, all I can do is I can reduce the grain size, I can make the material fine grained, and the strength of the material increases significantly, right? This is what we call nanocrystalline materials. So what people have done is people have made the crystalline materials polycrystalline materials whose grain size is of the order of tens of nanometers. so that there are so many grains in the material and the material behaves as if it is extremely strong or harder, right? So now as we reduce the grain size, the yield strength of the material is increasing. Stronger means what? That means it is difficult to impart flashy deformation. That means the yield strength of the material is increasing. So the yield strength of the material sigma y is given by sigma naught plus ky by root d. This is what we call the Hall-Petch relation, which represents the relation between yield strength and the grain size. So ky divided by root d, as you reduce the d value, that means grain size value, sigma y increases. And this is valid when the grain size is extremely small, and if the grain size becomes very much larger, because it is in the denominator, this value will become much smaller than this, and hence your yield strength will not change much. This is your coarse grained yield strength, and from that yield strength, if you reduce the grain size further and further, then what you will see is that the total yield strength is actual yield strength as a function of grain size is increasing. Here you can see 1 by root d. 1 by root d means if I am going from left to right, what am I doing? Am I increasing the grain size or reducing the grain size from left side to right side? Am I increasing my grain size or reducing my grain size when I go from left to right?
Reducing the grain size.
Reducing the grain size. As per this equation, you can see that this is my sigma naught and then it is increasing. So this is your coarse grained yield strength, and because I am reducing my grain size, I can see that my yield strength is increasing. This is yield strength versus grain size for a copper zinc alloy. That's a brass. Right? You can see yield strength significantly improved, right? It has gone 4 times from 50 to 200 by playing with the grain size of the material. This is what we call Hall-Petch relation.
Sir, one small question here.
Yes.
How do you change the grain size actually? Like,
So when let us say you are solidifying a material, right? You have a casting and then you solidify the material. When you are solidifying material, you will have a liquid will start becoming solid, but it will create several nuclei at various locations, correct? And each nucleus start becoming a solid locally, and then that is how you will have different grain orientations that we have looked at in the previous class, right?
Yeah.
Now, if you are doing very slow cooling, okay, extremely slow cooling, then what happens? Slow cooling rate is very low. Then you are giving enough time for diffusion to take place, isn't it?
yeah.
And hence from the nucleus, you will have larger and larger grain size happening if you have a very slow cooling rate. Instead of doing that, if you have a fast cooling rate, you don't have enough time for the diffusion to take place. And as a result, the grain size becomes smaller. And you will have several nuclei forming, and each of these nuclei will form their own grain, and hence your total grain size will reduce. Okay? So depending upon the cooling rate, you can influence the grain size. Is that clear?
Got it.
Yeah. All right. So now the question is, okay, you told me that this is a Hall-Petch relation. Very nice. If I reduce the grain size, I can increase the yield strength. So if I make the grain size to be 0, then my yield strength is going to be infinity. Isn't it?
Yeah.
But that does not make sense, right? What do you mean by grain size 0? That means there is no material. Isn't it? So,
Right.
So that means this Hall-Petch relation should not be working everywhere. It only works in a certain region. So equation is not valid for very large and extremely fine grains. So here one by reducing, you see that yield strength is increasing. Okay. And you will see, here yield strength is increasing as the grain size is reducing. And if it is beyond 10 nanometers, less than 10 nanometers approximately, then what happens is the material dimensions is becoming closer to the atomic dimensions. That means you will not have a crystal locally. You are actually not having a long range order anymore. So you cannot really see that as a crystal. And the second thing is that the grain boundaries are so close, and hence your deformation mechanism will not be any more dislocation slip. It is dominated by grain boundary sliding. So grain boundaries, because each grain is so small that imagining a long range order within that grain does not make sense, isn't it? And hence your Hall pitch relation does not work beyond certain value. This is what we call inverse Hall pitch, wherein the Hall pitch relation does not work, and again your yield strength starts decreasing. So there is only a certain region where yield strength keeps on increasing as you reduce the grain size. After that, again it starts decreasing. Okay. So if you further reduce the grain size, grains will be of the size of the unit cell, which destroys the long range order, and now the material is amorphous. It is not crystalline anymore. Then you cannot talk about plastic deformation through slip. You should be talking about plastic deformation through other mechanisms. Okay. Any questions there? So you understood how a nanocrystalline material is more stronger than a coarse grained counterpart. For example, nanocrystalline copper will be having higher yield strength compared to a coarse grained copper. Do you understand why it is low? It is so?
Yes, sir.
Yeah. So here I will give a couple of minutes. Those of you who have not followed can ask me now questions so that we can take everyone into confidence. So I will just open the class for discussion, because it's important that you understand these things. This question or anything else? You need to unmute yourself. If you are asking something, I will not see, because all of you have switched off your videos. So I will not know whether you are trying to speak or not. Okay, there seems to be no questions. So the next strengthening mechanism is what we call a solid solution strengthening. So first now, yeah.
Sorry, I had a question in twinning. So
Yeah.
whether twinning is like it just happens before the strengthening, like
No.
before one grain boundary.
No. See, twinning is another mechanism for plastic deformation. Plastic deformation can happen in two ways. First one is by dislocation motion. And the second one is, the dislocation motion is also called slip. Second one is twinning, wherein the atoms do not move over long distances. They will only move short distance in such a way that they become mirror images of another atom about a plane. So these are the two mechanisms in which plastic deformation takes place. And when the plastic deformation is taking place, you see that if you look at if you remember, we will talk about the mechanical properties, and then you say that first you measure the yield strength of the material. Then after yielding happens, plastic deformation started initiating. Plastic deformation gets initiated. You will need to apply larger force in order to continue further plastic deformation or further deformation in the material. That is what we call strengthening. Why? The material is becoming stronger after we actually achieved yielding in the material. The reason for it to become stronger is because these dislocations are interacting with the grain boundaries. When these dislocations interact with grain boundaries, the grain boundaries are offering resistance, and as a result, your strength of the material is increasing.
Got it. Thanks.
Yes. Now, grain boundaries are one kind of an impediment or one kind of obstacles to dislocation motion. So the idea is anything that is happily in a material, and if you create an obstacle, that obstacle will offer some resistance. As a result, you will see strength in the increase in strength of the material. And one such mechanism, another mechanism, is called solid solution strengthening. What is solid solution? Solid solution is nothing but alloying. If you have a pure metal, copper, and to that if you add nickel, nickel as an alloying element, but you have actually impured copper, which was otherwise a pure material. So this is what we call solid solution because they are in the solid state. The solution need not always be in the liquid state because whenever we say solution, liquid comes into our mind. But solution does not mean anything about the state of the matter. It is whether it can be in solid state, liquid state, or gaseous state. So we are talking about solid solutions. So alloying with impurity atoms that go into the either substitutional or interstitial locations will improve the strength and hardness. Why? Because the dislocations when they are moving, they see a new atom, that means the new stress field in the material, and hence they immediately need to adjust to the new stress field. That means you will see a resistance to the dislocation motion. And that is what we call a solid solution strengthening. Okay. So depending upon the type of impurity, if it is a small impurity or a large impurity, so then because of that, your local state of stress will change, and as a result, you will see an impediment to the dislocation motion. So if you look at the copper nickel system, so here you have a copper alloy, nickel is 0%. And if you measure the tensile strength of this copper nickel alloy, if it is pure copper, the yield strength is, tensile strength is, so let's look at the yield strength. I think tensile strength is not a good candidate to look at. Let us look at the yield strength. It is 70 megapascals for pure copper. To that pure copper, if you are adding 10% nickel, then you will see that the alloy strength is 100 megapascal. All right. So adding an impurity is not necessarily a bad thing to a material. You are actually able to increase the yield strength of the material. And if you further increase, you continue to add up to 50% nickel in copper, you have gone from 70 megapascals to close to 160 megapascals. Again, if you further add nickel, then again it starts decreasing because it becomes more nickel than copper. So what you would see is that if you have pure nickel, its yield strength will be somewhere here. Pure copper is somewhere here, but then alloy will have a higher yield strength. Why is that? Because of the solid solution strengthening. Okay. So the Placier deformation in polycrystalline materials, it is a complex deformation mechanism, and you have numerous grains in the materials, and each of these grains are randomly oriented. That means the crystallographic orientations are random. And for each grain, motion of the dislocation occur along the most favorable slip system. And the total or cross Placier deformation results is due to the distortion of the individual grains. And in this, grain boundaries play a major role, which will hinder the dislocation motion. Because there are more grains, you would see that the polycrystalline materials are usually stronger than single crystal counterparts. Because in single crystals, the dislocation impediment only happens due to dislocation interactions. But when you have a polycrystalline material, you can have dislocation interactions within a crystal, within a grain. In addition to that, you can also have dislocations motion is impeded by the grain boundaries. And hence, there is more resistance to dislocation motion in a polycrystalline material compared to a single crystal material. And as a result, you will have the polycrystalline materials are observed to be stronger than a single crystal material. So this is a polycrystalline copper. This is one grain, that is another grain. You can see that each grain is oriented differently, and as a result, your slip, these are all slip planes. The serrations represent the direction of the slip, and each one of them are oriented differently and different directions. That is what happens. The macroscopic Placier deformation that you would see is resultant of all these local Placier deformations in individual grains. That is slip system 1, slip system 2, and so on. Okay. So in a single crystal, work hardening is due to only work hardening or strain hardening is only due to the dislocation interaction, which would impede the dislocation motion. And if you have neighboring grains like polycrystals, and you will have multiple slip, and because you will have so many grains and you have slip acting happening at various grains at the same time. because depending upon the macroscopic loading direction, there are so many grains. It is possible that there are slip systems oriented in a favorable direction, meaning cos phi cos lambda being same for various grains. That means you can have parallel yielding initiating on more than one grains in a polycrystalline material. And as a result, you will not see in a polycrystalline material you will not see the stage 1. You will only have a very small stage 1. Immediately you will see hardening. The reason for that is there are multiple slip systems that are active at the same time, and there are so many grains and so many dislocations are interacting with the grains, and hence you will not see this easy glide in polycrystalline materials. As soon as the plastidiformation initiates, immediately they start interacting with the neighboring grains, and as a result you start seeing hardening from the beginning itself. Is that clear? Why in polycrystalline materials that easy glide is not there?
Yes,
Yes, sir. Yeah.
sir, one question.
Yes.
So we are saying that on solid strengthening process, so yield is increasing
Yield strength is
because of
increasing.
yield strength is increasing because of that impurity adding, and
Hmm.
in that case, like as we have seen before, in that case, like grain size, we are reducing, sir, in this case.
No, grain size reduction is independent of solid solution strengthening. In
Okay.
grain size, you can have a single material. It need
Okay.
not have other material. Even if it is a pure copper, because of the fact that you are adding, you have more grains, the dislocations come and interact with the grain boundary. But in a solid solution strengthening, even if you have, it can be single grain, but it can be two materials because of the fact that the second material is of different sized atom. As a result, you can have a local stress field that is getting altered, and when the dislocation sees that local variation in the local stress field, it needs to adjust to that variation in the local stress field, and hence it sees an resistance to the dislocation motion. That is the difference between solid solution strengthening and grain boundary hardening strengthening.
Okay. Yeah.
Yeah.
Thank you.
So when you are plastically deforming, what happens? There are more slip systems getting activated because there is the slip rotating during plastic deformation and so on. And hence, because there are more slip systems getting activated, more dislocations are moving. That means the number of dislocation are increasing in the system. That is represented by something called dislocation density rho. So the shear stress or the flow stress is represented by tau naught plus alpha GB square root rho, where rho is the dislocation density. As you increase the dislocation density, you will see that the flow stress increases or the shear stress increases. What is the reason? Because if you have more dislocations, the probability of these dislocations interacting with themselves as well as them interacting with the neighboring grains or the grain boundaries is much, much higher. And as a result, you will see the flow stress increasing as you increase the dislocation density. Okay? All right. So far, we talked about strengthening, how the material strength can increase. But it is also possible that sometimes the materials get softened. That means the softening mechanism. So this can happen under special circumstances wherein the materials can soften. One of the primary softening mechanisms is damage accumulation, meaning the material internally will lose its load carrying capacity by damage. That means the bonds are permanently broken, not re-established. See, in plastic deformation is what is happening. The bond is broken, but it is re-established with a neighboring grain. Imagine a scenario where the bond is completely broken. If they're completely broken and they are not re-establishing, that is what we call damage. So the damage accumulation can cause delamination in composites is one such example. That at that time you will see softening. That means with increase in strain, your stress will not increase, stress will reduce. There is another mechanism called geometric softening, which basically meaning, right? They rotate toward a crystallographic orientation for which the Smith factor is maximum. So imagine a scenario wherein all the grains are rotating in such a way, oriented along the loading direction, such that your Smith factor is maximum. Once the Smith factor becomes same for all the grains in a hypothetical situation, then until then the material is showing hardening because of the dislocation interaction. Suddenly the Smith factor has become so high. Suddenly you will not require so much high force, and hence you will see softening in the material. Another way that the softening can happen is thermal softening. That means if you are increasing the temperature, right? If you are further deforming the material plastic deformation will result in lot of energy that you are putting in the plastic deformation will result in heat dissipation. As a result, the material's temperature gets increased. So that increase in temperature can actually result in softening of the material. So these are the various softening mechanisms that you can have in the materials. So now let us look at this interesting question. So let us calculate the stored energy in a copper crystal. Suppose let us say you have a copper crystal with a dislocation density of 10 power 11 per centimeter square. How do you describe dislocation density? The dislocation density is described as total length of dislocations per unit volume of the material. So if you have so many dislocations, you count the length of all these dislocations per unit volume. That is how you define dislocation density. That is why length per volume give you per centimeter square. So you have 10 power 11 dislocations, 10 power 11 centimeter dislocation per a centimeter cube volume. That is what it means. 10 power 11 per centimeter square. This is typical for highly deformed metal. And then you have to calculate the stored energy in a dislocation in a copper crystal, and also calculate the total deformation energy per unit volume at a strain of 0.5 and compare that energy with the energy stored in dislocations. So you are applying some load. How much of that energy that you are putting in is stored in dislocation? How much is dissipated as heat? That is what we want to calculate. We know the shear modulus is 48.3 GPa and Burgers vector is 0.25 nanometers, and copper work hardening is given by sigma naught K epsilon power n and so on. So the dislocation energy per unit volume is given by half rho GB square. We have seen that G is the shear modulus, B is the Burgers vector. So the total dislocation energy per unit volume is 1.5 into 10 power 6 joule per meter cube. What is the total deformation energy? Because you are straining a material up to 0.5 strain. So integral sigma times sigma d epsilon will be total strain energy or deformation energy in the material. Sigma is given by sigma naught K epsilon power n, where epsilon is the strain. When you do that, you get 1.4 into 10 power 8 joule per meter cube. So that means when you are straining the material, the total deformation energy is this. Out of that, only this much is what is used for dislocation, right? That means the dislocation energy is only 1.4% of the total deformation energy. What is happening to the remaining energy? The remaining work is dissipated as heat, and as a result, the specimen temperature increases. So if some of you remember doing uniaxial tension test, if you have done the uniaxial tension test, at the end of the test, if you quickly touch the specimen, you will see the specimen is very hot, right? The reason for that is a large fraction of that energy that you have put in is dissipated as heat, and hence that might become hot. That is what increases the temperature of the material. Okay. All right. So with that, we have discussed the imperfections in materials, right? Which are dislocations in materials. And next we will talk about the mechanical properties. So what we have done so far in this class is we have started with understanding the structure of crystalline materials, and we have realized that, okay, structure cannot be perfect. We will have some defects, and there are two types of defects, actually three types of defects. Point defects, line defects, and two-dimensional. These are zero-dimensional defects, one-dimensional defects. Two-dimensional defects are grain boundaries or phase boundaries, and three-dimensional defects are pores. So that means a missing of atoms in certain volume. That can be a three-dimensional defect. Okay. So these are the various types of defects that we can have, but one-dimensional defects are extremely important for understanding plastic deformation. And hence we have spent some time on that, and we understood the concept of dislocation and the dislocation motion, which can explain the plastic deformation in materials. And we have seen that when the dislocation moves in a crystal, it can interact with other dislocations if it is a single crystal, or it can also interact with the boundaries of the grains if it is a polycrystalline material, or it can interact with other atoms of the material if it is a solid solution. The interaction of the dislocation with all these things is going to result in increase in yield strength of the material, right? So that's how we discussed about strengthening. And in the process, we have also discussed about a very important strengthening mechanism called grain boundary strengthening, through which we have introduced an interesting concept called strengthening of nanocrystalline materials. In the process, we have discussed about a Hall-Petch relation, which describes the relation between yield strength and the grain size of the material. And we have seen that as we reduce the grain size, the yield strength of the material increases, and that is the mechanism that is used in strengthening the nanocrystalline materials. Okay, and then we've also talked about solid solution strengthening, and any other foreign material that is sitting in the crystal will offer resistance to the dislocation motion, and that increases the strength of the material. And in the end, we also said that, okay, strengthening is quite common, but sometimes you will also see softening, and there are different kinds of softening responses. One softening could be due to damage accumulation, wherein bonds are permanently broken. And the second one could be geometric softening. What do I mean by geometric softening? When I am applying the load on a specimen, then the load, because of the applied load, the plastic deformation takes place in the various grains, and these grains try to rotate during the deformation. And imagine a scenario where their large fraction of these grains are oriented in such a way that the Smith factor on them becomes maximum, and then suddenly it becomes much easier for your system to get plastically deformed, and hence you will see a drop in yield strength because of the reorientation or rotation of the crystals. And we have also seen something called thermal softening, wherein the material, because during the plastic deformation, a large fraction of the energy is dissipated as heat, and that dissipated heat can increase the temperature of the specimen, which in turn reduces that increase in temperature, if it is not dissipated well, will increase the propensity of the dislocation motion. That means that you are providing more energy, and hence dislocations find it easy to move. So that is how thermal softening can take place. So these are, in a nutshell, this is what we have discussed as far as the plastic deformation is concerned in a material, right? And in the next module, what we are going to look at is how do we understand the mechanical properties of a material, because we try to measure the one important mechanical property, uniaxial tension test. We will look at in detail and then try to understand how the mechanical properties of various materials are measured and how do we make sense out of it and use that for assessing the failure in the material. Because in order to assess whether a material is going to fail or not, what we need to do is we need to ensure that we know what the mechanical property of the material which needs to be used for assessing the failure. What is that material? How do we measure that mechanical property is what we are going to look in the tomorrow's class. Okay, I think I don't think it's a good idea to start that module today, and we will start that module in tomorrow's class. Okay, any questions so far? Once the tomorrow's class is over, then I will give you your first assignment so that you can start working on the problems.
Professor, one general question, like what is the suggested book actually if you are suggesting?
So I would suggest there are two books. Mechanical Behavior of Materials by Mayers and Chawla. It's a very good book, and also Material Science and Engineering by William Callister. These two books are good. But I would say this Mechanical Behavior of Materials by Mayers and Chawla is good. And also there is another book called Mechanical Behavior of Materials by
Dowling.
Norman E. Dowling. Okay, that is also a good book. I have prepared
Sir, can
slides.
we get your presentation?
I have already shared. No? No,
Received, sir, unfortunately.
the
I
drive
think,
that our office has shared with you. Can you just log in and check while we are speaking?
Yeah, it's there
Yes.
for us, sir.
Yeah,
24
it is-
batch we got.
24 batch, 23 batch.
no, sir,
No,
we
sir,
are not getting it.
struggling.
Oh, both the okay. Okay, 1 minute. Let me see where